In this video, we're going to do a demonstration using simulation code through Matlab to model how the spring mass system works as we change the damping coefficient in the system. Just a reminder that what we're trying to do here is capture the motion of this mass up and down as it's being acted on by a spring and a damper that's dragging it slower. And we're trying to highlight this connection here where we explore what happens when there's no friction, when there's light friction, and then there's that critical damping threshold, and then we get heavy friction or heavy damping. What we are expecting to see graphically are these curves here where we have an undamped system, just means oscillating forever. And then as we have a little bit of friction, a little bit of damping, we expect to still see oscillations, but they decrease in magnitude with time. And then as we hit the critical threshold and go to overdamped, we should see essentially pure exponential decays happening with no oscillations whatsoever. So what we're going to do is explore that with specific values, k equals 25 and mass equals 1. And before you start, it's helpful to think, given that context of mass of 1 kilogram and a spring force of 25 newtons per meter, what damping level is going to trigger that transition between oscillations and overdamped behavior? What is that critical damping threshold? So think about the equation here for a moment, and then consider your answer among the ones listed. Okay, even if you don't remember the technical formula for it, you can go back to this quadratic formula and actually discover it. What we're interested in is whether we get complex answers to this root finding problem or whether we get pure real. And that all hinges on what's underneath this determinant. And if you see we have 4 times 25 here, that's 100. And so if our c squared is also 100, we're going to get exactly 0. It's going to be the transition between real and imaginary solutions, or real and complex solutions. So if c squared is 100, that would be c equals 10. So keep your eye on what happens as we approach c equals 10 in the modeling that we're doing. Think about what the solution should look like below that threshold and above that threshold. And as we go through the simulations, try to ask these kinds of questions about the mathematical form. We're going to be showing that on the screen, but keep an eye on that and how it relates to the C value. And also, does the graph change as we go through different stages of increasing the damping? So looking for the graph and mathematical form. All right, switching over to Matlab now. Here we have a simple simulation of oscillations that we get in the spring mass system if we have a mass of 1 kilogram, no damping whatsoever, and then a spring constant of 25. If you think back to where I could find the period of these kinds of oscillations, the period should be square root of m over k times 2 pi. That should end up being 2 pi over 5, which ends up being around 1.25 seconds. And if you take a careful look at when we complete one full cycle here, that's 1.25 seconds, 2.5 seconds, and factor around 5 seconds is 4 full cycles. So we have all of that built in here. So this graph shows literally the position of our mass over time. We get the period right based on the analyses we did earlier. And what we're going to do now is just gradually dial up the friction. So let's start off easy. We just add a little bit of friction, and you see the first change is that we start getting decay in the amplitude over time. So what we're doing is we're giving this a little kickstart. It goes up and then goes down, and then just oscillates. And because there's a little bit of drag, a little bit of damping, a little bit of friction, it goes down and down and down over time. How do we see that in the mathematics? In the solution we get, we end up with an exponential here. It's cos e to the minus 0.05 t. So there's this very slow exponential decay involved. If we kept this graph going on longer, we would see the amplitude peaks going down with this exponential decay. And as we dial this up just a little bit further, you'll see we get quicker decay in terms of the shape of the graph, and that corresponds to a larger coefficient of t in here for the exponential decay constant. And we keep going up, and 4, and 5. Again, the mathematical form doesn't change. All that is being updated as we change the friction coefficient or the damping coefficient to get slightly larger exponential decay factors. And notice we're nowhere near the transition to critical damping. Critical damping happens when this is 10. We're not even up to 1 yet, so let's start going a bit faster. This is where we start seeing quite rapid decay. So here we're kickstarting it, but there's enough damping that after 6 or 7 cycles, it's pretty much faded to, it's never 0, 0, but pretty close to 0 for all practical purposes. If we go up to 2, we start seeing even faster. Notice there's a minor change to the internal frequency. Before we had COS of 5.0T, now it's 4.9T, so there's a minor adjustment that happens there, but pretty small overall. The much bigger factor in play here is the fact that these peaks are decaying with now e to the negative 1.5T, so we get like 2 bounces out of this and then we're done. And what I want you to keep an eye on is notice we're not that close to 10. Let's go to 5. Even though we have a form that has cosines and sines still in it, in practice, if you were to observe this system from the outside and just not know anything about the math, and you saw this, how it goes up, down, and basically bounces and stops. So an important realization is that even though we're not mathematically at critical damping yet, the behavior we have looks pretty close to it. Why is that important? Well, because some people get kind of hung up on the critical damping as the mathematical transition and feels like it's some massive change of behavior. When you actually look at the graphs, it's not. Let me just compare 5, 10, and 15 here. So we do 5, we do 10. All that changes is we don't have that little bounce and then back again. Here we have our 2 solutions that are exponential decay only, so mathematically it's very different, but just going back to 5 for a second, those, in terms of the observer's perspective of the actual behavior, are not that much different. So even though there's a massive mathematical transition from imaginary or complex roots to all real roots, it's actually smoother than that in practice. So let's do our 10 again. And then when we go to 15, say, what you see there actually was a slight extension. Keep an eye on this graph here. We'll go back to 10. That's 10. And just look how quickly it's decaying down. As we get higher and higher, the damping is so strong that it's actually hard for the system to move back down towards 0. We're getting strong resistance to that. And the larger we make these numbers, the slower the system is to get back to 0, just because it's like moving through sludge. This is the 25 damping factor here would be like really cold oil in a door spring system, door damping system. So 15, we get closer at the critical damping. We do get that fast, relatively fast response back towards 0 without any bouncing. Let's just go to 9 just to see. 9, though you can't see it, it does actually have cosines and sines in the solutions. In practice, that bounce is so overwhelmed by the rapid exponential decay that you can't see it. So anywhere from 9 to 10 to 11, even as we go over the mathematical transformation from complex solutions to real solutions, we don't see a massive transition in the graphical side, which is good because from our physics perspective, from our physical intuition, just dialing up the friction coefficient shouldn't radically change the behavior. And in fact, it doesn't do that. We instead see in practice that transition from, we see oscillations that gradually decrease, decrease faster, decrease faster, decrease faster still. And then by the time we get to 4, approaching the critical damping, they damp out very quickly. We get to 5, and then basically we're not even getting a bounce anymore. And then we hit critical damping, and there's no oscillations at all in the math or in the graph. And after that, it just becomes, as I said, like moving through very cold oil in a damping system. And that's it. So the fun part about this in my mind is that we can now, again, predict. We can predict the behavior of some system that we've never seen in real life, may not have been manufactured yet, but if we know the important quantitative elements of it, if we know the spring constant over here, if we know the damping coefficient, if we know the mass, or if we get to design those, we can select the behavior that we want the system to demonstrate. Or with an existing system, we can predict what kinds of behaviors it's going to elicit or show or demonstrate for us in the real world. For those who find this at all interesting, the next step that we take is not just to limit this to the behavior of a system that we kick and then let it go. What we start doing is turning this into control theory, where we say, well, what if I could add a motor to this? Could I get this spring mass system to do something else? Can I get it to oscillate at some other period, even though its natural behavior is to oscillate here at a fixed frequency based on C and K? The mathematics that we've seen so far can easily be extended, or relatively easily extended, to handle that case where we add another outside force, which is our motor control, and then we can do some even more fun things in terms of our simulations and predictions.